All right, let's see. Let's go live here. Make me choose all this. Stop. So many screens. Live on that. Good, that's going. This is good. Use a category, education. Sweet. All right, we're live on everything. That's good. Took a while. Riplaw and Grim. What's up, guys? Fortnite. Yes, Fortnite is today. Fortnite do be today. We do like Fortnite. Say on God. What do you mean say on God? Oh, this sausage is very full of things.
What's up, Van Gogh?
What's up, dude? That's dope. I'm starving. I haven't eaten anything today. And I was like, shit, I gotta go stream.
Fat ass.
I know. Well, I'm not fat ass. This is the only thing I've eaten today.
Like, can you hold off till stream is over?
Yeah, no, because then we have Fortnite, and then after that I have to go teach. So like, this is literally like my one option to like eat. It's my window, dude.
Guys, let's make a rule now. You need channel points whenever Gold wants to eat. You gotta pay for Gold's food.
What's up, Ethan? Noise says, I have a sexy question for you. I'm gonna have to do the working for it. I'm down. Hi, Teacup. What's going on? What's up? A lot of other people in the chat. Cool. Lots of stuff. Man, it's been busy last couple days. Nick keeps spamming some cat emoji or something in the Discord.
Yeah, I see Nick keeps spamming that shit. You gotta fix that.
I told him to stop. If they don't, I'll just remove it. Yeah, that's too funny. I don't know. You know what it is, Grim? It's because they found something that annoys you. You know how when you find something that annoys someone and you keep pestering with it, they found something that annoys you.
I don't get annoyed by it because I actually have something to focus on other than Discord. I don't really get annoyed by it. Oh, I went to the hospital last night.
Oh no! Why'd you go to the hospital? What's up, Rocky?
Some dumb thing. Something dumb I did.
Something that you did?
Yeah, something dumb that I did.
Did you break something? You cut something? What happened? Was it appropriate?
No.
Okay. Well, you can send me a DM about it later then.
I broke my dick.
No, don't say that, Grim. Grim, we're on Twitch, please.
I'm kidding. I didn't break my, But no, I did something dumb.
Okay. All right. Well, I hope you're better.
I don't really care about the emojis. I just care if they're if I'm trying to have a conversation and they're literally spamming it.
Mm-hmm.
And I'm pretty sure that annoys everyone.
I agree.
And go.
I don't like spamming channels.
If you look right here in the syllabus, it says don't spam, press troll.
Correct. I agree.
In gold and gray.
Yeah, you're right. You're right. You're right. Well, they're not mods. I mean, they're assistant mods. Which, yeah, maybe I have to take that away next. I don't know. It's Noise was talking about this. He's like, why do all the mods fight with each other? I'm like, because they get like some sense of power and then they just want to like take it out on each other. I don't know.
I don't even have one still over here.
I know, because there's less fights. That's why. All right.
And what? Then why do I fight then?
I don't know. I don't know why people fight. Y'all kids. you know. Oh, this was fun. This was all the stuff we did with Noise Noise. Who was here over the weekend? Who got to see Noise Noise and I? Noise Noise actually taught me a lot about like elementary particles. I had a really good time with this.
I was here.
You were there? Yeah, dope, dude. Did you guys like get anything out of this? You know, must have been at least interesting, right? I don't know. Physics is dope. That's what I did for my PhD. I can't. All right, here, let's load up some questions. Oh, Noise, did you want to do part of your exam? I know your exam's coming up on Wednesday. I said I'd maybe do like one of your questions as well. You let me know if you have something else you want to go through. Let me see, who has the first question? Oh, Riplaw does. Oh, cool. Oh, let's go through all this. We don't need this. Back. No. So many pages. There we go. Okay. All right. Start off. Welcome, everyone, to Office Hours. My name is Dr. Gold. This is Actual Education, stream that helps you out with math, homework, science homework, all types of fun stuff. Noise Noise, it's okay. You already said math question. Okay, cool. Awesome. Username joined. What's up, username? We got 4 people on TikTok. What's up, guys? For those of you that are new to us, this is a live stream where, like, I'm basically a free math and science tutor or physics tutor, whatever you need help with. We go over questions here live on the stream. You can learn some stuff along the way. We make it fun, and then if you guys want to join our Discord, you can actually earn prizes for asking questions. I think Riplaw, you got the next tier too, didn't you? You got the next tier, right? Nice. Yeah, I'll get that to you later today. We do it after we do all the streams. But yes, excellent example, Riplaw, of how, like, if you just show up and you're consistent, you get prizes, you get rewards. It's awesome. Oh, thank you. Someone liked the live. That's cool. Okay. All right, let's see. This is a cool concept. Do you know what this is? Do you know what this is, Riplaw? There's a name for this. It starts with a T. Starts with a T. What would you call it? There's something after this. What do you call it?
I don't know how to say it, but I know it's better.
Okay. It's called a transversal, is what this is. Have you heard that term before?
I typed in chat.
Oh, yeah, good. Oh, you did type it. Yeah, very good, Rip. Thanks, dude. Yeah. So anytime you have 2 parallel lines, and you have a line crossing it, this line crossing it is called a transversal. And there are some important properties of transversals. We have what's called, like, the corresponding sides, right? We know those. What does it mean for 2 sides to be corresponding?
I don't know.
Okay. Corresponding means if I look at, for instance, like, let's say I make a square where the transversal hits each one of my parallel lines. Do you see how I could break this up into, like, quadrants? Like 1. Let's use some different colors here. 2, 3, and 4. Do you see that? You see that, Riplaw?
Yes.
Okay. So what corresponding angles means is that the same area of this quadrant on each other, they're equal to each other. So, one sec. Let me copy. Whatever, fine. So, for instance, this part of the quadrant, this angle, is equal to this angle as well. So these quadrants are equal to each other. Yeah. Candace says, is it 55? Candace, have you already solved it? That's too cool. We'll see. We'll see. Anyways, those are corresponding sides. Which, that's what we have here, right? If we look at this question here, Rip, right? Do you see how this side is corresponding to this side because it's in the same part of the same part of the quadrant?
Yes.
Okay, so how do we solve for x here then? What do we do? I think Candace is right.
Add 5 both sides.
Well, first we got to set them equal to each other, right? We know this is equal to this, so you want to write this out as an algebra expression. I want to say 2x minus 5 is equal to 105. And then, yes, you add 5 to each side. Cool. 2x is equal to 110. What's the next step?
Since we want the x to be by itself, do we like divide by 2?
Yeah, very good. In algebra, anytime you see like the variable and you're trying to get it by itself, look what's happening to it. In this case, x is being multiplied by 2. So I'm going to do the opposite of multiplication. I'm going to do division. So right, I'm going to divide by 2. Divide by 2. I get x is 110 over 2. Do you know what 110 over 2 is? He's like, I'm going to go get the calculator. I know. You don't need the calculator for this one. You know what 100 divided by 2 is, right? What's 100 divided by 2? $100 divided by 2 would be 50. And so 110 is just an additional 10, right? So I like to think, okay, 100 divided by 2 is 50. 10 divided by 2, that's equal to 5. So all I need to do is add these up, right? I have 100 over 2. This is just a good math trick for you just to know how to like do things in your head. This is the same thing as 110 over 2, which is the same as 50 plus 5. So your final answer is, and you are right, Candace, it's 55. Good job. Cool. It's like a geometry question. Are you in geometry, Rip?
I passed that.
Oh, you passed that? Okay. What math class are you in right now? What are you in now? Are you in pre-calc?
I've been just doing higher level questions.
Okay. Cool. Well, that's awesome. Yeah, and you know, I can always like help you out with like higher level stuff and whatnot. That's a great way to get ahead. And then when you get to your math classes later, you'd be like, I already know this shit. You know, I'm good. Cool. Good job, Rip. I'll get you your Robux later today. Cool. All right, you're welcome, dude. All right, nice. All right, let's see. Next one is trash can. Trash can's next. Ooh, we're gonna do some dilations. Ooh, this is fun. I like dilations. Not this. Grim. God damn it, Grim. Yeah, I'm taking forever to upload. Do 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 do. This must be like the most high resolution photo ever. I'm taking forever to upload it for some reason. Yes, Ethan, do a physics question. Yeah, we did a lot of cool physics on Saturday. It was fun. But it was kind of like last minute, yeah. All right, here we go. Well, let's see. Where's trash can? Trash here. Come to the stage, trash. Boom, 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 boom. Says graph and label the dilated image ABC using a scale factor of 3 using the origin as the center of dilation. Oh, this is cool. I like this stuff. This stuff is dope. Trash can, how do I do this? How do you think you do this one? It's a good question. Oh, can I wave to people here on TikTok? Can I just wave? Oh, no, can't wave to them. I wanted to wave to them. Trash can, where you at? I'm gonna put Mr. Bean, dude. Mr. Bean's gonna be waiting for you, dude. Bum, 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 bum. All right, moving on. Teacup, what's up? Teacup, you here? Where's Teacup? Where's the cup of tea? Characteristic polynomials. I might need your help on this one, Noise. Or hopefully Ramton's getting better. I think he was sick for the last couple days. Oh, Trash Can said BRB. Okay, so he's out for a bit. All right, that's fine. All right. Next up, I'm gonna do Noise's question because I like seeing these. Okay, cool. This is a calculus question. Noise. I'm not sure with respect to the y matters. It might. Let's see. I assume this is supposed to be cosecant of x. Is this just like the British way that they write cosec? Like we do this in America. We say CSC. We say CSC of x. Okay. Find the integral using u substitution. U substitution's cool. Yeah, cosec is just cosec. Okay, cool. Got it. All right. So this is the integral of cosecant of x dx, which what we know from our trig days is that it's pretty grotty. All right, we'll see. Is that cosecant is the same as 1 over sine. And the other one you guys should know is that secant of x is equal to 1 over cosine. It's kind of backwards. You see how there's a cosecant, cosine, but secant, right? Secant sine. I never know why they did that. I feel like they just did that to like confuse us. Like, why isn't cosecant 1 over cosine and secant 1 over sine? Because cotangent, right, is 1 over tangent. That would make sense to me, you know? If someone knows the mathematical reason why they do this, I don't know, but it just is. Okay, that's fine. So, I'm going to say, okay, this is the integral of 1 over sine of x dx. And they want me to use the u substitution of cosine of x. Okay. Let's see what happens here. Okay, so if u is equal to cosine of x, then du is equal to derivative of cosine is negative sine of x dx. Oh, this is pretty cool. Look at this. I actually do like this. Okay. So dx is equal to du over negative sine of x. Okay, got it. All right. No, we'll do yours next, Teacup. I was waiting for you, but I didn't see you. Okay, so I'm gonna plug that into here. Oh, this is kind of gross though. What? Because this is the integral of du over negative sine squared of x. I don't like that. Really don't like that. How are you supposed to do this with this substitution here? Noise. Because first of all, this is in terms of x, so this is bad. You don't want to use a u substitution where I don't get rid of the x. Solutions in office hours? Let me check it. I'm curious. Is this for your math class? Is this for your math class? Okay. I think I see where this is going. Okay. Yes. Okay. Yeah. Okay. This is all right because yeah, I'm going to use this identity. Sine squared of x plus cosine squared of x is equal to 1, right? So sine squared of x is equal to 1 minus cosine squared of x, or negative sine squared of x is equal to cosine squared of x minus 1. Okay. All right, I'm okay with this. This is, yeah, that's weird. That's weird to do that. I guess you can. I've never seen them do this type of stuff, but okay. This is a good trig identity everyone should know. It's a very important one. I know that there's like a huge list of like infinite amount of like trig identities, but this is like one of the most important ones you should know. So yes, I'm now going to replace this with this. So this goes away. Goodbye. And this is cosine squared x minus 1. And then cosine squared of x is the same thing as u squared. See how u squared is equal to cosine squared? That's nice. Okay. So then this is du u squared minus 1. Which I believe this is... Now this is a trig substitution. Is it not? Yeah, I think it's a trig substitution one now. Because... I gotta remember these sometimes. There's a lot of them. Let's see. Trig substitution integral. I forget if when it's u squared minus 1. I think it's secant. All Okay. No, that's the square root. When is it u squared minus 1? Or you know what I think it is? I think it's arc. It's the arc trig things. Inverse trig integrals. That's the one I'm looking for. Yes, here we go. This is what it is. No, it's square root of a squared minus u squared though. Huh. Oh, I see noise. Yeah, no, that works too. Man, this is a pain in the ass. This one, dude. What? Yeah, real pain in the ass. Oh, why is Discord loading again? Discord, go back. You're okay. Okay. So yeah, what I'm gonna do. This is gonna become partial fractions now. Is what this is gonna become. Because I'm gonna write u squared minus 1. This is another, again, important algebra thing to know. If you have a squared minus b squared, this is the same thing as a plus b times a minus b. This is what they call a difference of squares, right? Okay. So in order to do that one, I have u squared minus 1. So that means a is u, b is 1. So this is going to become u plus 1, u minus 1. Okay. All right. So now we can write this as the integral of du over u plus 1 times u minus 1. And now this is partial fraction decomposition, in which I know, for instance, if I have something with a bunch of factors on it, let's say 1 over u minus 1, u plus 1, I can rewrite this as a over u minus 1 plus b times u plus 1. Yeah, partial fractions, very important to remember this one as well. So, in order to solve for what these coefficients of a and b are, I'm going to multiply both sides by the denominator here. I'm going to multiply it by u minus 1, u plus 1. I'm going to do that on both sides. Let's take it here. All right, Control C. We're going to multiply by that one, and we're going to multiply by this one. Okay? So, in doing so, this will cancel with this. So this just becomes 1. So I get 1, because these all cancel, is equal to the u minus 1 is going to cancel the u minus 1 here. So I have a u plus 1 plus, and then it's b, and the u plus 1 cancels, and then this is u minus 1. All right. So I can distribute this out. This is au plus a plus bu minus b, and I'm going to group them by powers of u. So this really looks like 0 times u to the 1 plus 1 times u to the 0. U to the 0 is the same thing as just 1, right? And then this is going to be equal to a plus b. Or here, let me make the colors the same. This is a plus b. Oh, my mic is super hot. One sec, let me fix that. Okay, that'll be better. Sorry. Y'all tell me if my mic is like super crazy. It's Windows is the worst, dude. They reset my mic settings like constantly. Okay. This is a plus b times u to the 1. And then plus, so we got rid of that, and then it's a minus b times u to the 0. Aha. Okay, very cool. This is kind of fun? Yeah! I'm glad Cardenas. Yeah, that's the whole point. Like, kind of make a game out of it. It's fun. Math doesn't have to suck, This is kind of a puzzle. Because what I notice is that I should have the same coefficient in front of each power of u. So u to the 1 has a 0, so this also should be 0. So I say, okay, 0 equals a plus b. That's cool. And then in front of the u to the 0, which is just a 1, I should have a minus b. So I have 1 is equal to a minus b. Okay. So if I add these together, so this is a systems of equations I can solve. Yeah, you're an EE. That's cool, man. Yeah, electrical engineering is dope. I got my PhD in plasma physics, so I basically did a lot of electrical engineering. I did a lot of circuits, and actually a lot of EE kids were actually in some of my plasma classes, which is cool. But But anyways, you add this, right? This cancel. This is the, I think they call this the elimination method for solving a systems of equations. But basically, if you add these two things together, you get 1 is equal to 2a, and then these go away. Goodbye. So I get a is equal to 1/2. And if a equals 1/2, then b has to equal minus 1/2. Cool. All right. Now we can go way, way up here. And we can rewrite this whole thing as the integral of, and what, let's see, which one was over the u minus 1 was the a, and that's going to be positive 1/2. So that's going to be 1 over 2 u minus 1 plus integral of negative 1 over 2 u plus 1 du. Excellent. Okay. These are now going to be, basically, if you have the integral of du over u, it's equal to ln of u. But this is, you know, kind of it's like another u substitution. Maybe we call it v substitution at this point. Because this is really the integral of 1 over, or actually, no, you know what it is? You know, fuck it. Let's just pull the 1/2 out. We can pull the 1/2 out. 1/2 out. We can make this a minus. We can pull the 1/2 out. Okay, cool. Gone. Okay, so now this is 1/2, and then it's going to be, this is going to be the ln of u minus 1 minus the ln of u plus 1. And then again, this is why I know all you guys are saying, like, why do I learn all these things in math? Like, why do I learn about log rules, you know, in pre-calc or whatnot? It's because now I need to remember my log rules, which is whenever I have, for instance, the ln of a minus the ln of b, this is equal to the ln of a over b. So this whole thing becomes 1/2 ln of u minus 1 over u plus 1. Okay, cool. And then the last thing is probably to do the trig sub, where that was, u was equal to cosine of x. So this should be 1/2 ln of cosine of x minus 1 over cosine of x plus 1. And if you want to put the 1/2 back in, because again, if you have a ln of b, this is the same thing as ln of b to the a. I can put the exponent back up. And so this would be the ln of all of this to the 1/2, and to the 1/2 is a square root. So it's really this, cosine x minus 1 over cosine of x plus 1. I think that's the final answer. Let's see if it is. Let's see, what is that? Dun, dun, dun. Yes, we're flipped though. We're flipped on a sign. Why are we flipped on a sign here, Noise? Did I forget a minus? Maybe I forgot a minus. Let me check. I want to check this one. Actually, you know what I can do? Wolfram Alpha is the best. I can just get Wolfram down. Just curious. Wolfram Alpha. So integrate cosecant. Oh, they do the half angles? I don't want the half angles. Oh man, that's so gross. Why are they doing the half angles? Ugh. What are the half angle approximations? Wait, was it? Sine of over 2. What is that? Another half angle approximation. No. 1 over cosecant of x over 2. Oh, okay, this works. It's 1 minus cosine of it. Okay, so they have the 1 minus on the top. Is that what I had? I cosine of x minus 1. Okay. I'm missing a negative sign somewhere. Okay. Symbolab better? Is Symbolab really better? Anyways. I talking about I've been who's inviting me to speaker? Oh.
Anyone want to speak?
No, I do want you to speak. Oh, Discord's like messing up. What the hell? What the hell? One sec, give me a second. Discord screwed up. There you go. Okay, that's better. Why does it say like? Yeah, why was I not the speaker? Oh, Discord just screwed up. That's all good. Okay, cool. Yeah. Good. All right, that's it. Good job. Okay, nice. Yeah, sorry, Discord reset and it took me off the stage for some reason. That's so weird. I was like, why am I being invited to my own Discord stage? Okay, cool. I don't know why I did that. That's why we always have it on the Twitch, so you can also watch on the Twitch too. If I have time, Noise, I'll do the second part of your question next. Yeah, that was a cool question. I enjoyed that. Lots of use substitution stuff. All right, let's see. What's up, Ramton? How's it going, brother? You feeling better? Feeling better?
Yeah, I
Did you get COVID? Did you get COVID like I did?
I don't think so. I think I've just if I got it, then it's pretty mild. Like I haven't had any symptoms other than a little bit of congestion.
Did you get the fatigue?
Oh no, I don't think I have it because I don't have any of the symptoms compared to last time. Like, no fever, nothing.
Well, that's good.
I think it might be more of an allergy because, like, I think it's just my sinuses and my throat.
Yeah, I can tell. Yeah, your nose sounds a little congested. I'm always like confused whether it's like allergies or if I'm sick or something. I can't tell half the time.
Yeah.
I had COVID last week.
How's it going? No.
You had COVID last week. What is that? What happened, Gagu? You had COVID? Oh no, dude. I'm sorry about that.
It was horrible.
Yeah, it's not fun.
I couldn't do anything.
You couldn't do anything. Yeah, did your brain felt like it was in like a microwave or something?
Yeah. It was super hot.
Yeah, I had a big fever too. Yeah. Yeah, COVID's not fun. I've had it 3 times now at this point, so like I don't know. I'm kind of over it. Like, can we stop getting COVID? Oh man. All right, let's see. Is Trash Can? Are you back in the audience? Yeah. All right, cool. All right. Let's do your question. You're good, dude.
Is
All right.
Trash Can a new part of the crew?
I mean, he's been in this Discord for a bit. I think Trash Can's been here longer than you have.
Yeah, I think so.
I think so. I think he's been, yeah. Okay, Trash, how do we do this one? What is this? Graph and label the dilated image. This is fun. Scale factors.
So what I think is that we multiply the triangle by 3.
Yeah, what do you mean multiply the triangle by 3, though?
By 3.
Good, yes, yeah, you do multiply each, yeah. So, what they want you to do, right? Do you see how they say here, like, pre-image and, like, image?
Yeah, so the pre-image is the normal A, B, and C.
Mm-hmm.
The A prime, A, B prime, and C prime are dilated image after it's dilated by the scale factor.
Exactly. And then there's an important thing here. Because they're using the origin as the center of dilation, that's the only reason you're allowed to just multiply all the coordinates by 3. Yeah.
Oh, so
if it's not, I don't know if it's not. There's probably a more complicated equation for having to dilate things. I think what you end up having to do is creating what's called like a vector from this, whatever the point is, to where the center of dilation is, and then you need to increase the size of that vector by whatever the dilation factor is, and then find out where the new point is.
Okay.
You're not going to have to do that in your level of math. I know in your level, they're usually just going to say the origin is the center of dilation. Noise says vectors. Yeah, oh no. I could do it, but it'd be a little advanced. Okay. So pre-image coordinates, right? Do we know how to label coordinates? Like, where's this coordinate A?
-2, comma 1.
Yeah, nice. Good. Then B is what? What's that? 1, 3, I think? Yeah, right? I'm trying to like read this. Then C is 1, 2 over. Then 1, 2, 3, 3 down. Okay, 2 minus 3. Right. And so, yeah, what'd you say we do for the image coordinates? What do we do next? Right, okay, we're going to multiply all these by 3. So negative 2 times 3 is going to be negative 6. 1 times 3 is going to be 3. This is going to be 3 comma 9. And then this is going to be 6 comma minus 9. So if we wanted to graph our new points, this would actually be pretty cool. So you can see what it looks like. 1, 2, 3, 4, 5, 6. 1, 2, 3. So this becomes like 8. Let me get like something that's, maybe I just need it bigger. Or maybe red? Maybe red would... No, red doesn't look better. I'm trying to think, like, what looks good on this background? We're going to do this. We're going to call this A prime. And then 3 comma 9. So we go 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. And then this is going to be B prime. This is a thing that carries over actually in all classes, like math and physics and whatnot. Prime usually means like afterwards. So usually, if we're going from A to A prime, this is like before, this is afterwards. You'll see this in physics. They do this a lot with positions and all sorts of things. Okay, and then C goes 4, 5, 6, and it goes down 9. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. Oh, wow. All right, so this is going to be big. So now we got this big, massive triangle that has been extended, right, by a factor of 3. Cool. Yeah, all good. All right, nice. Good job, Trash Can, dude. That's a good question.
Yeah.
Sweet. All right, let's see. Who's next? Teacup, are you in? Are you in the audience? The audience, Teacup. There he is. Oh, there you go. Nice. Ooh, asking more matrix questions. Yeah.
Ooh, matrix.
Is this the eigenvector one? Is that what this is? I forget which one this is. Rampton. What is this? What's the characteristic polynomial again? Yeah. Noise is like Rampton time. He's been missing you. Noise has been missing Rampton, honestly. He's like, where's Rampton been? Yeah.
I'm glad I'm able to help. Yeah, the characteristic polynomial is the determinant of the matrix minus, or the determinant of A minus lambda I.
That's right. That's right.
Yeah, so this being like the matrix A, and then lambda I, where I is the corresponding
eigenvalues, right? Matrix. Oh, sorry. Yeah, and these end up being the eigenvalues, I think, right?
Yeah. So like once you take the determinant of that, you can set that to be equal to 0, and then the solution to, or all of the values of lambda are gonna give you your what's it called? Your
eigenvalues and eigenvectors, I think, right? Yeah.
And then I don't know. This might be more interesting for noise, but
yeah.
If you have what they call degenerate.
Oh yeah, degenerate. Yeah, we were talking about. Oh, did you see what we did a stream this weekend, Rampton, on little elementary particles?
Like, yeah, I saw
all this stuff.
Noise was talking about like the.
I learned a lot. I learned about a lot about hadrons and leptons. I was like, oh, what is all this stuff?
Yeah, these are some cool stuff. I know to that extent, but
yeah.
I didn't take particle physics, so I kind of just like brushed over some of the
right. Concepts. To me, I thought it was interesting because I thought it was like taxonomy, right, of physics.
Yeah.
This is kind of where like biology starts like influencing physics. You're like, oh, we're just gonna start classifying things. Okay.
Yeah.
Yeah. But degeneracy is a thing in quantum, right? Degenerate. I think I was mentioning that, like if something is degenerate, you know.
Yeah, I think. Yeah, there's something that is degeneracy is a thing in quantum. Yeah, and then I guess like another thing when they say degenerative, it means that there is more than one power for your lambda, right? So like, let's say when we find, or I guess what they call degeneracy.
Yes.
So right now, if you've solved the solution to this, like once you take the determinant, you set it to 0, you would factorize and you would find all different values of lambda.
Right.
And so let's say, because this is a 3x3, you expect 3 values of lambda. Let's say you find 2, right? It means that your solution, let's say one of them, like lambda equals to 2, let's say, for example.
Sure.
Lambda equals to 3. When you factor it out, it's going to be like, let's say lambda minus 1 times lambda minus 3 to the power of 2. And then so it has a degeneracy of 2. So there's going to be 2 associated, let's say you have something like that.
Yeah, say that's
so
what it
the
is.
Lambda minus 3, or lambda equals to 3, essentially has a degeneracy of 2. And so there's going to be 2 eigenvalues that are associated with this.
Okay. Now, what does that mean? Does that mean there are 2 separate eigenvectors?
Yeah. There's going to be 2 separate eigenvectors.
Oh, okay.
That are associated. I think maybe I said 2 eigenvalues. I meant to say 2 eigenvectors. You're right.
Oh, okay. Sorry. Yeah, sorry. It's the same eigenvalue, right? Because it's the eigenvalue is 3 and 3, but each one of them has a different eigenvector.
Yeah. So when you have something like this, which I don't know if a lot of people have seen this, then when you put it into the format where they call like a eigenvalue decomposition, it's not gonna work anymore. So you have to do this thing called a Jordan canonical form.
Okay.
Where it's gonna look a little bit funky, and then so instead of having your eigenvalues across the diagonal, you would have like your eigenvalues, but then one of them would be eigenvalue 1, 0, eigenvalue.
Okay, let me see if I can get just like, because I like all these terms. Like I didn't know there was like a standard eigenvalue eigenvector form for things. Let me see if I can just like get the determinant of this one.
Typically, the problems that are given are gonna have different.
Or let's find one where there is a degeneracy here. Let me just find a problem where there is a degeneracy. Eigen.
Yeah.
What would this be? Degenerate here. Degenerate. Eigenvector problem. Someone give me something. Okay, here we go. This is one they give. Let's see if this actually turns out to be degenerate, because I'm curious. I want to work through this. This is actually a good one. And these are nice numbers. So we have 7, 0, 6, 0, minus 5, 0, and then I think that's 6, 2. I don't have to watch this person's YouTube.
So.
Oh, this is done by some. Okay, and then he has 6, 0, minus 2. Okay. So if we were to solve this doing the regular well, wait one second. Yes, 7, 0, 6, 0, minus 5, 0, 6, 0, minus 2. Good. Yes. So if we end up doing, for instance, this is matrix A, and we do matrix A minus lambda I, that's going to be 7 minus lambda, 0, 6, 0, minus 5 minus lambda, 0, 6, 0, minus 2 minus lambda. And then we take the determinant of this, okay? This is the whole T method. Luckily, there are a bunch of zeros here, which will make things nice. So this becomes 7 minus lambda, times minus 5 minus lambda times minus 2 minus lambda. And then this whole column goes away because this is just 0, which is nice. And then this one is plus 6. Okay, but this one goes away, so it's just minus 6 times 6, so minus 36. Negative 5 minus lambda is equal to 0. Aha. Okay. And there should be 3 lambdas, but let's see which ones there are. So
Yeah.
I see.
So there's gonna be a minus 5 minus lambda that you can factor
Right.
it out
Mm-hmm.
from the whole thing.
Yeah, you're right.
And then it's gonna be multiplied to the multiplication of the two things
Mm-hmm.
minus 36.
I see. Okay.
Yeah.
So then we need either lambda is equal to minus 5. That's okay. Or this whole thing is equal to 36, right?
Yeah, I guess we'll look
Lambda-
at the values of that. Yeah, so
Okay, let's see. Minus 14. And then what's that? That's plus 5 lambda. I think that's right?
Yeah.
Okay. And if this has to all equal to 36, so subtract, right?
Minus lambda.
Is it, we have minus lambda. That should be lambda squared, no?
Yeah.
Oh.
You have
Okay, yeah, sorry.
Plus-
Say it.
Yeah, you have plus 5 lambda.
Uh-huh.
Should be minus 5 lambda because it's 7 times minus lambda and
Uh-huh.
then minus lambda times.
Yes, you're right,
minus 2.
yeah. I got screwed up with this being on the right side.
Yeah.
Yeah, okay. And then, but then this is right,
Okay.
minus 14, and this has to equal 36, so if I move this over, this becomes minus 50. Okay. Oh, and then this is factorable, right? Because what two things add up to negative 50?
5 and 10.
Right? Yeah, 5,
So
5,
it's
5, and
gonna
minus
be
10.
Minus 5.
Oh, that's so cool. Oh, yeah. Okay, cool. So you get lambda plus 5, lambda minus 10. So this is another lambda is equal to minus 5 solution, and then this is lambda is equal to 10. Oh, very cool. Okay.
Yeah, so then it has a degeneracy 2. So if you look at the eigenvalue decomposition of this, like I think maybe there is, I can do this online.
Mm-hmm.
Eigenvalue decomposition.
Yeah, and they call this second order degenerate. That's the key thing here. They call it second. Noisoy said, this is why you miss Rampton. Yeah.
Yeah.
More advanced math.
So then let's see if I can eigenvalue calculator. Or I guess
Well, we need the vectors is what we need, right? Because now what we have is we have what is it? We have 7, 0, 6, 0, minus 5, 0, 6, 0, minus 2. And then this is all supposed to be times vector, like, right, this vector. And then this equals to negative 5 times the other vector. This is the whole A vector is equal to lambda vector. This is kind of the whole eigenvalue thing.
Yeah, or actually then there's another way that you can do this is like it's what they call like the kernel, which is like the kernel is the null space, another way of saying it. Is just the null space of A minus 5i. So you can find it that way as well. So I guess I can hop on the
hop on it. Yeah, write some stuff. You're good.
Attach. No. It's another cool way of doing it. Okay.
Yeah, because I know with this method you can then just do like a big systems of equations, but you know, it gets kind of messy sometimes. Like that.
I did my reading final today. I probably failed.
No, dude. What? You didn't fail, dude. You're okay. You're fine, dude.
All right, so we found so that's one way of doing it.
Uh-huh.
I guess we can do it both ways, or I can do, or another way.
You show the new way because I know you've shown the other way before, which is all good.
Yeah, so it's the kernel of a minus I guess the lambda in here is -5, so I'm gonna write it as I guess maybe I'll just write -5.
Okay.
Minus
Right.
5.
So another way, it's the kernel of a plus 5i.
Okay.
I guess I wrote equal to 0, but that implies it.
Mhm.
So the kernel of this, so first let's find a plus 5y. So it's going to be 12, 0, 6, 0, 0,
Mhm.
0, and 6, 0, 3.
3. Okay.
So and we can clearly see that this is just 2 times the first one as well. So this is going to give us...
Oh, I see. This is degenerate because this is basically this.
Yeah.
Ah.
So we can reduce. So this is equivalent to 12, 0, 6, 0, 0, 0, 0, 0, 0. And we can rewrite this one in terms of 12. Sorry, 2, 0, 1, 0, 0, 0, 0, 0, 0.
Yeah.
And then typically in here, you want to have like a free so you would have like a free variable kind of thing. So let's say we call if we have x3, here our x3 is going to be our free variable. So 2 times x1 plus x3 needs to be 0. So then...
Oh, I see. You're calling this x1, you're calling this x2, and this x3,
Yeah.
like these whole
Yeah.
this whole. Okay. And then Teacup, what happened here? Teacup, this is a little bit of a linear algebra thing. If you can always take different rows and you can add them to each other in different multiples. So what Rampton did is he multiplied this one by -2. Okay. See how that becomes -12, 0, -6, and then he added this to it, which is why it became 0, 0, 0. That's the whole thing about matrices and manipulating them. You can add rows and you can do whatever like multiplication you need to do to the entire row. And that's what happened here is because this was 12, 0, 6, so he multiplied the entire row by 1/6. And that's why 12 divided by 6 went to 2, 0 divided by 6 is 0, and then 6 divided by 1 is just 1. Okay? Now he's left to here. All right, keep going, Rampton. You got it.
Yeah. So then... Sorry. So yeah, once we find the kernel of this, then in here you should have like 2 different variables. One of them, I guess, is gonna be the x3, so that's one free variable. And then so our first vector is gonna be -1/2, 0, 1.
Okay, so when we say taking the kernel, you're trying to set this equal to basically all zeros? Is that what this is, basically?
Yeah, all zeros, exactly.
Okay.
Yeah.
Oh, okay. This times some x1, x2, x3 needs to equal 0. Is that kind of what we're getting at?
Exactly.
Got it. Okay.
Exactly. So then...
I ordered a mouse pad.
All right, I'm glad you ordered a mouse pad. But yes,
Totally
it's all good. It's all good. This is matrix multiplication. Remember how we do this times this plus this times this plus this times this? Yes.
Yeah.
That's important. Important to know. Okay. So that's where Rampton got this from. He got 2x1 plus x3 is 0, and then 2x1 is equal... Oh, you just simplified this down is what you did. Okay, I see.
Yeah.
Okay.
And then you can always write this, this is like, you can write this as -1, 0, 2 as well.
Sure.
Right? As long as it's any multiples of it.
Right.
So one common practice is to put this into a normalized form. So you would just divide it by its
magnitude, right?
Magnitude. And the magnitude of this is square root of 5 because it's just square root of 1 squared plus 2 squared. So you can say your first degenerate eigenvalue is -1/(2). square root of 5,
Mm-hmm.
0, and then 2 over square root of 5.
Okay.
Right? And then another thing is, if you have any vector which is in the format of 0x0, this is going to give us multiplied by this vector, or multiplied by this matrix in here, it's going to give us 0, right? Because 12, or I guess I can call it 201, 0, 0, 0, 0, 0, 0. If I multiply this by anything which is in the format of 0x0,
yeah,
you can
it's
see
always gonna be 0.
it's always going to just come out 0.
Right. Okay.
So another factor of this is going to be 0, I guess
1
0.
0. Right. Yeah, that's the normalized
Because we
form.
want to normalize it, right? So
very cool.
so yeah, you're gonna get 2 different
So these are the 2 different eigenvectors for the eigenvalue lambda is equal to -5.
yeah, exactly.
Very cool.
Yeah.
Yeah.
And then
wow.
once you do that, you have to put it into what they call like a Jordan canonical form, which is, it's that one's kind of a deep dive on, I guess, something a little bit more complicated.
Mm-hmm.
But I guess just to show like what's the necessity of that is that I want to make sure that.
Yeah. The other way, Teacup, you could have seen this is that in order for x1 plus x3 this to equal to 0, you could have just set this equal to 0, this equal to 0, and then x2 can be anything. So that's why but there's another thing called normalizing, which means that you want the magnitude of these things. These also kind of look like they are vectors, but they look almost like a distance per se, where if you just divide it by the magnitude, which is the length of the vector, then yeah, this would just have to be 1. That comes out. It's cool. That's very cool. I'm learning some stuff. But I'm curious, what's this Jordan canonical form?
So I just want to let me quickly just put this into a calculator.
Yeah, you're good.
Just so that I can make sure.
Yeah, make sure it's right. You're good. You're good.
Solve this correctly, just so that we don't have to backtrack.
Someone in the TikTok sent 5 roses. I don't know what roses are on TikTok. Is that a form of currency? Is it like bits? Someone tell me.
Gold, you just made $50,000.
Yeah, right. Is every rose worth $10,000? That'd be dope. I take it.
I'll take it.
Oh man.
All right. Yeah. So once you find this exactly, so do you know what's the eigen decomposition? I guess.
I probably do, but I forgot. Remind me.
Okay. So the eigen decomposition is just like when you put the matrix A into this format, P inverse lambda P.
Okay.
Or sorry, I think it's P lambda inverse P. I always forget this, but then you can always figure it out by.
Well, aren't you? You're acting this on V inverse, right?
Yeah. So it would be.
How does that work? Sorry.
Yeah. So it would be P inverse here.
Right. Got it.
Yeah.
Cool.
Okay. So then I'm also gonna just check just to make sure I can.
Yeah, inverses are cool. We like inverses. This is why I always tell the students when I have like 5x, this is the same thing as like 1 over 5 times it's 5 inverse. Kills it off.
Yeah, that makes sense.
Yeah.
Okay. All right. So then once we have this, essentially your P in here, or the lambda is the matrix that has all your eigenvalues in there across the diagonal. So one of the eigenvalues of this we found was -5. And then the first one, what was it?
-5 and 10.
It was 10. Okay. So we can put it as 10, 0, 0, 0, -5, 0, 0, 0, -5. And then your P is going to be is gonna be.
Yeah, don't they put it? They put the vectors like this, right? Is that what they do?
Yeah, so they will put it like that. So the first one is gonna be associated with your first eigenvalue, whatever that may be.
Yeah, whatever that was.
And
Yeah.
then you can put the other ones, which is 0, 1, 0, and then -2, or say -1 over square root of 5.
Right.
0, 2 over
2 square root of 5. Okay, cool.
Now, what I what I believe is going to happen is that if you do this, you will not get back your original A. Because it's supposed to be in what's called a Jordan canonical form. And the reason is because this eigenvalue decomposition only works, if I'm not mistaken, for when you have all different eigenvalues. And so the Jordan canonical form puts this into a format which, instead of big lambda, they put J. So you need to put it as 0 or 10, 0, 0, 0, -5, 1, 0, -5. And then you have a Jordan block in here.
Okay.
Essentially. And the size of this Jordan block is going to be dependent on the degeneracy. So if this was like, let's say, a 5x5 matrix, and then we have a Jordan block of size 3, then it's going to be like a Jordan block where it's like -5, 0, 1, like that. And then there is, let's say, another one that has another degeneracy of 2. So you're going to have like 2 different Jordan blocks. So essentially, when you have degeneracies that are 1, you essentially have these Jordan blocks already. But each Jordan block has a size of 1. But then, as you have more degeneracies, the Jordan block sizes end up going up.
I see. So if you had multiple degenerate eigenvalues, we only had one degenerate eigenvalue, and it was ordered. Does the order matter? Like what the order of the degeneracy is?
Like which way they.
Well, like say for instance, the eigenvalue -5 had a degeneracy of 3. Would that change like the size? I guess that would be like this, right?
Yeah, then it would be the 3x3 Jordan block.
Gotcha.
Yeah. So then.
And then this is a 1. Is that what you're saying? This is a 1?
Yeah, that's a 1. So typically you have a 0.
Yeah.
Because it has degeneracies of, but then Jordan blocks have like a 1 sitting there.
Oh, okay. That's cool.
And this happens when you have like more than degeneracies, which this is actually like I actually never got taught this in undergrad.
Is this just like self-study? You just like went exploring?
Yeah, so I was studying essentially nonlinear systems. And so when you have nonlinear systems, sometimes you could have things called saddle points.
Okay.
Right? And I guess that one really, like, I really like the nonlinear systems because it kind of uses like a variety of different topics. Because first you talk about differential equations, then you talk about solving differential equations that are in like systems, which are matrices.
Yeah.
So you solve like a differential equations with like a matrix in it. So you have like e to the power of like a matrix. And then to find the solution of that, you have to use Taylor expansions.
Oh God.
It
gets more and more complicated.
The matrix itself needs to be like the first order approximations near a fixed point. So you have to talk about what fixed points are. Then you talk about eigenvalues and eigen vectors and what their interpretations are. And then so when you have a saddle point, then you start to get these things. So saddle points are points that are attractive in one way. So a system tends to go towards that state from one direction and tends to go away from it in the other direction. Right? So you can think of like an X and Y axis, right?
Sure.
Let's say if you're along the Y axis, you would gravitate towards a certain state. And if you're along the X axis, you would divert from that state.
Yeah. The saddle points are because it's because the second derivative is like different, right? Going one way versus the other, basically. Which axis you're going on?
I think so. Yeah.
Here, let me show an example of a saddle point to the kids so they can kind of see. Because it says, yeah, some people are like, you're like, what is all this stuff? No, this is very cool stuff. It has to do with, here, let me get this image.
So if you put saddle points in like
Okay, this is an example, guys. Of do you see how this kind of looks like a saddle? Right, looks like a horse saddle. You know, if like someone was sitting here, they're like, oh yeah, I'm gonna ride the horse. Yeah, right. Okay, cool. What Rampton's talking about? So like, say this is a 3-dimensional object, and then there are 2 axes here. For instance, this could be the x-axis, and this could be the y-axis. And what happens is if you take a slice like down here. Well, here, let's change the color. Let's make it pink. If I go this way, like for instance, along the y-axis, I end up hitting like a minimum here, which means that like anything off of this saddle point, I will gravitate towards it as I travel along this axis y. However, if I travel along the x-axis, right, which would be like in this direction, now any point away from the saddle point, you fall off, which is like unstable. And that's what he talks about when we talk about like gravitating towards or gravitating away from. Rip says, I understand nothing. Well, Ripple, I hope you understand what a saddle is. You know what a saddle is? This is what a saddle point looks like.
A good picture for
yeah, you got another pic? Yeah, you can paste it in. Okay. Yeah, okay. I like this one. I got it. I'll zoom in on it.
Yeah. If you can get it, make it big. Oh, there we go. Yeah, so when you have a saddle point like this, you can see like from one way, you kind of get close to it, and then you go along the other asymptote, you kind of get away from it. So depending on like, you have 2 different directions along this. Essentially, let me put it with green. So as you can see, this axis is your attractive one, and this axis is going to be your repulsive one. So this is what they call a fixed point. Right? Because if you're sitting at that point, you're not going to go anywhere.
Right. But if you move slightly along one of the axes, you'll either like come back or you'll fall off.
Yeah, exactly. So then they talk about the stability of this fixed point, and then you say that there are going to be 2 different directions of this. If you along these axes, you would diverge,
and you get like you get flipped out.
So then this is associated with a positive eigenvalue. And this is kind of comes from the fact that if you have e to the lambda t, right, that's going to be the behavior of it. So if the lambda is positive, you're going to diverge away from it. And then if you're going towards it, then this is going to be a negative eigenvalue. And then the directions of this, so this is going to be e to the, I guess, lambda t, but then where lambda is negative. And then the directions of these are your eigenvectors. So that's the I guess importance of eigenvectors as well, right? Where you have some kind of a.
Someone was asking, so you did applied math, Rampton? What does this apply to in the real world? Like, why in the real world are we finding stability along different directions with vectors and values?
So there is a whole bunch of different categories of this has applications in math, biology,
like predator-prey models, maybe, you know?
Yeah, predator-prey model is actually one of them. So if you have, like, let's say populations, and you want to figure out whether these populations end up kind of like, let's say you have a predator and prey, right? Would these end up having some kind of a cycle between them going back and forth? Or would one of these eventually win, right? So if people wanted to look at this, there's a thing called the Lotka-Volterra model.
Oh, I see. I got a picture of it.
Volterra model. So yeah, there's 2 versions of this, where there's the predator prey. There is the predator prey, and then there is the interspecies competition.
Yeah. This stuff, guys, is very cool for describing how, for instance, you know, when you have like mice and like hawks, or you know, even like tigers and I don't know, like deer. There's you can model, like, for instance, if there's too many tigers, then there's not enough food, so the tigers start dying. But then if there aren't enough tigers to eat the deer, then the deer start multiplying too much, and it follows like a whole. Oh, the hare lynx, that's a good one.
Yeah, that's the classic one they use. So
Okay.
if you can see in here, the prey, in this
Which I think they
one,
call the presa. I think it's supposed to be
Yeah,
Spanish
presa.
or Italian.
yeah. So then this one, their population will increase, right? This is the rate of population.
Sure.
So the more of them there is, which is the N1 being the population itself, times a rate, which is R1, depends on, you know, like how often they mate, how many children they have,
Right.
all these stuff, right? So it's just like a number you observe from nature.
Yep.
And so that's Rn1. And then there is going to be, this is how their population will increase. And then this is called the logistic model also, pretty much.
Yeah.
And then their population will decrease because of the interaction between the predator and the prey.
N2 is the number of predators. So, yeah, see, that goes up, right? As N2 goes up, then this negative starts to get bigger because there's more lynxes.
Exactly.
Yeah.
And then
is this the interspecies competition right here?
No, that one comes from the fact that the population itself would decrease naturally. So it would look like, let's say you had, what's it called? You will have, this one actually comes from the fact that it looks like this. It's R1 N1 times 1 minus N1 over like some factor.
Yeah.
And then essentially what this says is that if the population is going up, when there is little population, it will go up. But then when the population density starts to reach into, I guess this is more of a population density rather than the population itself, because there is a kind of I guess, scaling that needs to be done. So, and then the reason is because if you leave even rabbits on Earth, they can't just, you know,
eventually run out of food.
Yeah, exactly.
You got too many rabbits, so like, we don't have enough food to eat. Like, uh-oh.
Yeah, then it comes from this kind of. It's like a R1 times N times 1 minus.
I see, the 1 minus N1. And then,
they divide by a thing.
Some critical factor.
Saturation density.
Yes, okay. Saturation density. That makes sense, yeah.
Yeah. And then that's pretty much like, I guess you just only do the second part and all that stuff. But yeah, so the whole point of that is that, you know, you can't have population past a certain point because, you know, just the nature itself cannot.
And so these also have like stabilities where, for instance, like there's a nice happy medium where there's a certain number of predator and prey, but sometimes there are scenarios where it's an unstable equilibrium where you're saying that, for instance, the prey just gets completely wiped out or the predator just gets completely wiped out.
Yeah, pretty much.
Oh,
and then
cool.
So with this model, and then you can see that the predator increase their population depending on their own population and the prey's population.
Right.
And then it would naturally decrease because the natural thing without the prey, they would just die off.
It would just die off.
Right?
Yeah, because the prey are their food. It's literally their food. They don't have any food, they just die.
Exactly. So then if you look at the solutions of this, you can like look at the stable points of this. And then the stable point is when both of these are 0, essentially.
Okay.
Right? Which
when the change is 0. Right. Yeah, exactly. Okay.
Yeah. The rate, there's no rate of change for that thing.
That's equilibrium.
And then, exactly. And then you linearize this. So you find around you find the solutions for like the values of N1 and N2, and then you what they call linearize around that point. And then you look at their behaviors. And then there's going to be eigenvalues and eigenvectors associated with it. So eigenvalues represent kind of the behavior, and then eigenvectors represent the direction. Like which way would this win? So if you look at the predator-prey model, if you draw this, so it's going to be like, you know, let's say the prey versus the predator, this is called a phase diagram, I guess.
Mm-hmm.
Where you're not looking, because typically you see in here it's going to be population versus time.
Right.
So a phase diagram when you have no time in there.
Yeah.
Essentially.
It's just like the steady state solution.
Yeah, exactly. And then their populations are going to kind of look like this.
Uh-huh.
So these are the different states it could be. So depending on where you start on this diagram,
yeah,
you're going to get stuck into a cycle where they go back and forth.
I see.
So the solutions of this, the lambdas are going to be imaginary.
And this is interesting. So people probably can also relate to this. If you guys have ever seen, for instance, like an altitude map, if you guys have ever seen one of those, you know, if you're looking at a map and it shows like how high the mountain is and whatnot, kind of the same thing. The contour graph, I guess, is what it's called.
Yeah, exactly. Contour.
That's super cool.
Yeah.
Wow.
But yeah, like, so if you have imaginary things, then they would cycle. So like, this is the one for the predator and prey model. If you look at the interspecies, well, with that one, so another one, which is the rabbit and what's it called? Rabbit and sheep.
Rabbit and sheep.
Yes, because they both.
Because the rabbits don't eat the sheep.
No. The competition is over grass.
Oh, that's cool. Rabbits eat grass, sheep eat grass, and they're competing. Okay, got it.
Yeah. So with that one, you're gonna end up having like some kind of a stable point, or sorry, some of a saddle point. And with that one, essentially what it means, depending on their factors, like and then the important thing becomes what populations do these just start off as. So, and then how fast do they reproduce, like how fast do they eat, and all these stuff. Exactly. So when you have something like that, you could end up having one of the populations go extinct, or you could end up coexisting.
I see. So everyone's happy here, but then you could have extinction in either direction. That's cool.
Yeah, and it kind of depends, because you can also flip these two things. Like with that one, you have to break it case by case, because there would be 3 different cases where they might not even cross one another.
Right.
And so one of them just straight up goes into like extinction, like without even competing.
Oh man, this is too funny, dude. Yeah, so yeah, people who were asking, they were asking like, wait, what's the point of this? This is the point of it. You can use math. And this, I had a discussion about this, Ramton, I think on the last stream or something. Someone was asking about the hierarchies of science and whatnot, right? And I was saying, oh yeah, biology is just like super applied biochemistry, it's applied chemistry, applied physics. But really, see, biology is just applied math. Like all these things with the rabbits and the tigers and everything and the lynxes living, it's all based on math. Like it's all a numbers game. Literally is a numbers game. That's super cool.
Asked the question.
That's super cool. That's super cool. Yeah. So do you see how this relates, Ethan? Do you see how like we're using math and like numbers and whatnot to describe how animals are surviving?
The predator and the prey.
Yeah, predator prey, right?
This is what I guess one of the simpler things to explain, but you're gonna have like really big matrices, so you can actually predict what's it called, final state, like weather. You can do weather predictions using the stock market. Do gene what's it called, gene analysis, like how long a gene can survive in like a population. And in physics, it's gonna have like pretty much, you're always talking about like stability of states. So there's a lot of applications.
There's a lot of applications. Yeah, that's super cool. Awesome, dude. I appreciate that explanation, Ramton. That was really cool, dude. And I appreciate the question, Noise. Hopefully you guys learned some stuff from that. I learned some stuff. Noise says math is king. Math is king, dude. It is. I agree. What's up, brother?
You want to do my physics question?
I am gonna do. One sec. Fun and Learn is next. Let me get Fun and Learn. He's been waiting for a while. Fun and Learn, come to the stage. Question taking decades. Well, you know, that's why you got to ask your question first. Otherwise, you got to wait. Let's see if he shows up. Fun and learn. Okay.
I think he's trying to join the audience. I think he's trying to join the speaker.
Oh, I did. I tried. I invited him to speak. He says he can't speak. Okay, that's all right. We got Helen Keller here. That's okay. All right. Let's see. Okay, but you still have to type Fun and Learn. I'm not just gonna do your question. You have to at least interact on the text. Cool. Okay. He says all right. Cool. All right. Find the average rate of change of k of x is equal to x plus 2 over the interval 10 to negative 3. Good question. Do you know how to do this one? Do you know what average rate of change is? Kind of a cool thing. Says I don't know. That's all right. Okay. A good thing to do here is to graph this. So, for instance, this is the graph y. Yeah, it's okay. It's new. Do you know how to graph this? Fun and Learn. Do you know how to graph y is equal to x plus 2? Mm-hmm. Yeah, what does this mean in terms of a graph? One is y and the other is x. That's true. True. Yeah. This is y. This is x. Yeah, you could graph this in terms of points. For one y, there are two x's. Not quite. Not quite. No. So here, this is called a function. Fun and Learn. That's okay. We're gonna live your namesake, dude. You're gonna learn today. X and y points. All right. I can put in values for x. Let's say, for instance, x is equal to 0. Okay. If x was equal to 0, what does y equal now? Two. Good. Exactly, dude. Yes, perfect. Okay, so here's a point. 0, 2. All right. I can plug in another point. Let's say, for instance, let's plug in x is equal to negative 3. Okay. What is y going to equal then? Input and output. Yes. Very good. Very good. Yes. X is the input. Y is the output. Good. Output. That's a very smart way to think of it. This. Away. Okay. Negative 1. Good. Exactly. Okay, cool. All right. So these are points you could plot. So for instance, 0, 2 would be 0 here, right? And be going up 2. There's 0, 2. Okay, and then if I wanted to plot negative 3, minus 1, right? I go over to 3, go down 1. That's our next point, okay? This, if you have 2 points, and it's what we say is a linear, like a line. So for instance, it just has x, no exponents or anything on it. You can connect these 2 points, okay? And that's going to give you a line. This is the equation of a line. Things that are unique to lines, right, is that they have a y-intercept. Y-intercept is where this line crosses the y-axis, okay? That's here at y equals 2. And then the other thing they have is what's called a slope. Do you know what a slope is? Good to see you, Noise. Toodles, toodles, toodles. Yeah. The slope is like how steep something is, okay? So when they ask you for what's the average rate of change over an interval, they're asking you for what's the average slope. Rate of change, this is the same thing here as slope, is what it is. For a line, the slope is the same everywhere, which is nice. And actually, you can just look at this equation and figure out what the slope is. And I'll show you how. But sometimes you won't have a line. Sometimes you'll have a curve. So let's say, for instance, you had a curve that was, you know, something like this. Yeah, y1, y2. Good, we're getting there. Let's say this was my curve, and I wanted the average rate of change between x equals 1 and let's say, like, x is equal to 3, okay? In that case, the average rate of change is going to be the slope of what we call the secant line. The secant line is a line that connects 2 points on a curve. It's called a secant line. I know this. You probably haven't gone through this, but I just want to, you know, have you see the terms first, so that eventually you'll get it when you get to the higher math classes. Good. Yes. And so if I want to calculate the slope, I need to know 2 points, right? Slope we know is equal to y2 minus y1 over x2 minus x1. Okay. And so when they say the average rate of change over an interval, they want you to find the 2 points. They want you to find the point when x is equal to -3 and the point when x is equal to -10. Okay. That's another point we need to figure out. So if I figure out x is equal to -10, what is y going to equal? I need to move my graph over. Graph is not long enough. Good. Yeah, -10 plus 2. Very good. Very good, dude. What's -10 plus 2? -8. -8. Very good. Very good, dude. Yeah. Okay, cool. All right, so these are our 2 points, okay? So I have -3, comma, -1. And I have -10, comma, -8. And all I need to do is now find the slope in between these 2 points, okay? That's really like down here. Okay, so how are we going to find the slope? How are we going to find the slope there? Between this point and this point. Remember, we have this equation here. Sometimes it helps for me to label things. I'm going to call this, like, for instance, x1, x2. Or, sorry, y2. And I'm going to call this, sorry, x1, y1. I'm going to call this x2, y2. And then you can take this and you can plug in to find the slope. Well, let's try to see what it would be. So -8 minus -1. Good. Divided by -10 minus -3. Good. Wait a minute. Are we doing this right? I know the slope is 1, Rampton. What did I do wrong here? Oh, man. -3. No, this is right. What am I doing?
Wait, sorry. I like zoned out.
I zoned out too, dude. Yeah, bro. It's just finding the slope between 2 points. Oh, no. I'm dumb. Sorry. I got it. You're totally okay. This is my brain frying after like an hour and a half of streaming. It's okay. Yeah. -8 minus. Okay, this is a good question. Fun to learn. What happens when I minus a negative? I was looking at this and I thought it was gonna be like 9/7 or something, and I'm like, no, that's wrong. But no, it's okay. Yeah. How do we do this one? Fun. How do we do this one? Negative minus a negative is a negative. Kind of. But this is negative. Negative minus a negative. Well, it'll still be negative, but the key thing you want to know here, Fun, is that whenever you have minus a negative, you can make these both positives. So this is really -8 plus 1. Because I could have -3 minus -6, and technically this would be positive. Because this would go to plus, and then this would become 3. Because -3 plus 6 is 3. So -7. Very good. Right, very good. -7. all over. And then what's this? What's negative 10 minus negative 3? Negative 13. Close. Again, let's remember here. What do I do when I have minus and negative? Turn to positive. Exactly. This goes positive. So it's negative 10 plus 3 now. What's that going to be equal to? Negative 7. Good. This is also negative 7. Okay. You see how my slope is negative 7 divided by negative 7? Yeah, what's negative 7 over negative 7? One! Yes, good job, dude. Very nice, dude. Congrats. Yes, the average rate of change here is just going to be 1. That's what you're going to say. You're going to say it's equal to 1. You could also see this fun and learn by this equation. So y equals x plus 2 looks like the standard. We call this like slope-intercept form for a line. Y is equal to mx plus b. Okay? In this case, m is the slope. And if there's nothing in front of the x, we assume there's just a 1. So slope, m, is 1 in this case, which for a line, the slope is the same everywhere. So that's always going to be the average rate of change. Cool? I think it was a cool question. Fun and learn. Good job, dude. All right, let's see. Last question of the day. I'm exhausted. Let's pull it in. Ethan, what's up?
Yeah, I'm here.
Okay. Ooh. See, little physics question. Do some physics. Physics. Ugh. 103 views on TikTok. That's cool. Nice. Take it.
You know, I got this one off the internet, you know.
That's good. Self-exploration and learning is great. Always good, dude. Okay. Ultraviolet light of wavelength 103 nanometers, I think. Oh, was it millimeters? Millimeters?
Isn't it micrometers? It says it at the bottom, at the last part.
Oh, okay. Micrometers, yeah, that's
nanometers, because
yeah, right. Yeah, ultraviolet is nanometers, right? That's what I thought. Yeah, he wrote nanometers here, right?
Oh,
yeah. It's okay, Ethan. You've probably never seen this before. You've probably never seen what a nanometer is. Okay.
No, I've seen that. I've also seen that on the question, but I thought they mixed it up for millimeters.
Yeah, no. Nanometer is 1 × 10 to the minus 9. This is scientific notation. Another thing I'm not sure if you've gone through yet, but it basically means we move the decimal to the left 9 times. Okay. So
I have taken scientific notation.
Oh, you have? Okay. Then yeah, this is 103 × 10 to the minus 9 meters. Okay. Is incident on 2 narrow slits that are a distance of 0.352 millimeters apart. Okay. What is a path length difference for the n equals 4 reference line in micrometers? Ah, that's cool, man. The double slit experiment. You remember? Did I go over this with you? You know, I kind of did this during. Sorry, were you here for Saturday's stream, Ethan, with Noise?
No, I wasn't.
Okay, cool. Well, yeah, no, I literally went over something like that, which is cool. Here, I'll show it. I'll show what it is. Okay. This has to do with the double slit experiment, which means when we have light traveling in this direction and it hits like these two gaps here, right? They're going to make these waves, kind of like ripples. You know, have you ever dropped like a rock in like a thing of water?
And then it'll just show some splashes, like
yeah, some splashes. Yeah, and you see how they this is called propagating. They propagate away, like they move away from a center, right?
Yeah, because like I know that the force of the when you drop a rock into the water, you start to see circle things that pop out from it.
Good. Yeah, those are waves. Those are waves. Yeah. So light behaves the same way sometimes. Well, all the time, but there's all this particle wave duality stuff, but light behaves like a wave as well. So imagine like dropping a rock here and dropping a rock here, okay? And then them creating these circular waves from that center point, right?
Yeah.
What ends up happening is that these waves will interfere with each other. So for instance, you may get like a big part of this wave also lining up with a big part of this wave. Those two interact with each other in what we call interference. And specifically when they're both going up, this is what we call positive interference, okay?
All right.
And this makes a bigger wave. Okay, this makes big, oh dear. Bigger wave. Sometimes they can interact such that one has a wave going up and one has a wave going down. That's called negative interference. And that gets you nothing. Or a smaller wave, really. Yeah. Okay. Now, the same thing happens in the double slit experiment. When you have light waves emitting from these two openings here, and then let's say we put a screen over here on the other side, these waves are going to interact at this distance over here in different ways. Like, for instance, whenever you have like an up and an up lining up with each other from here and here, this is going to cause a bright spot. And then whenever you have an up and a down interacting here, for instance, this is going to cause a small spot, okay? And this happens repeatedly because waves repeat themselves. So for instance, let's say Ethan, I have two waves like this. Let's say this is what we call two waves that are in phase, the red one and the blue one, right?
All right, I see those.
Look what happens if I start moving one over. Do you see how now these ones are like an up and a down?
Oh, they're causing a negative one now?
Good, yes. This causes a negative interference, and they
make a small spot.
They make a small spot, exactly, yes. Now here's the cool thing, is that, so what I drew here is called one period. Period means like one cycle. But let me draw like a couple periods, just so we can see what happens, okay? Because this does repeat itself, which is pretty cool. Okay, so you can see, for instance, right, if this red wave moves this way, right? Because let's say the red wave starts later, or it has more distance to travel. That's what they call like a path length difference. Do you see how this will cause negative interference, right?
All right, I see that.
Okay, but look what happens if I move it even further. Then what happens?
Now it's almost lining up with that.
Good. This would be positive interference. This would make the waves be even bigger here, right? These get even bigger, okay? Now, the key thing, this goes on forever, Ethan. Like, I can keep moving this, like, on and on and on. And the different points at which this happens are what we call ends. So, for instance, this is n is equal to 0 is when it's like this. If we move it over again, this is n equals 1. And we move it over again, this is equal to n equals 2. Okay?
Mm-hmm.
So what that's telling you is that, like, something repeats a bunch of different times, okay? All right. Now, again, I don't want to get too heavy into, like, the math of how this works, but there's an equation here that describes... Do you see how, for instance, this top this top hole here, right, has to travel this distance, but the bottom one has to travel this distance, which is like much longer or a little bit longer, right?
Yeah.
There's a difference between, right? If I were to take this red one and like put it on top of the blue one, this ends up being the difference in what we call the path length, which means that when I put my waves on top of each other, for instance, the blue one and the red one, the blue one is gonna start later, right? See how it's gonna start later, which means or here we could say here starting later, for instance. So that's gonna create an interference pattern at different places. Okay. In order for there to be a maximum, I need the distance, like the head start that one of the waves gets. I need that to equal what's called a integer number of wavelengths. This is defined as one wavelength. We say 1 lambda. What it is, okay?
1 lambda.
Lambda means wavelength. So if I move this wave from here to its next starting point, and the distance from starting point to starting point is lambda, that's 1 wavelength. So this is why we call this n equals 1. I'm moving it 1 lambda. But I could then move it. Good. I could move it 2 lambda. You see, I could move it 2 lambdas, right?
Yeah.
And I would still get the same interference pattern, right? Okay.
All right.
I can explain the trigonometry later, like why this happens. There's some trig stuff.
I don't know trigonometry. I don't know trigonometry.
I know. So let's gloss over it. I'm gonna hand wave on that. I'm just gonna give you the formula for it, and then I can go on a later lesson to teach you about the trigonometry behind it. But basically, what they say is that in order for there to be a what was the question you were asking? What is the path length difference? Okay, very cool. All right. So in order for us to hit the n equals 4 interference pattern, I need to move this red wave 4 lambdas over. Okay. Where lambda is the wavelength of the line, okay? And let's see. Which one is the distance? Yeah, okay.
Also, what does that look like? What does that look like an upside down Y?
Because that's just what it is. Yeah, it's a Greek symbol. It's called lambda. Okay. So, do they just want the path difference? Sorry, what is the path length difference? Oh, I don't really care about the distance between the 2 slits. I don't think I do. Yeah, no. Okay. Yeah, okay. So it's just 4 times the wavelength. So the wavelength, you see how they said the wavelength here was 103 nanometers, right?
Yeah.
So we're going to do 4 times 103 nanometers. Okay.
4 times 103 nanometers. And then, wait, can I try this next one?
Oh, like trying to put it into micrometers?
Yeah, like
okay,
maybe
good.
you
Yeah,
try
show
and
show me how.
And then you divide the. I don't think you do the 10 negative 9 all over 1 nanometer.
So this is meters. So we want to divide this by the number of micrometers. Sorry, number of micrometers. So 1 meter is equal to 10 to the minus 6. Sorry, no. 1 micrometer is equal to 10 to the minus 6 meters. That's the conversion thing we know.
All right.
Okay. So how can I convert this into micrometers? This is like a stoichiometry question.
I mean, this is a little tricky since I'm not understanding most of it.
It's okay. Well, this is just a units conversion, right? At this point, I'm trying to convert meters into micrometers. Okay.
Wait, hold on. Let me think.
All right, think about it. You gotta do.
I think you gotta multiply by like the Let me see. I think you multiply by 10 over 6 or something. 10 to the 6th power.
You can multiply it by 10 to the 6, or you can. So here's what you can do: is I can say that okay, 10 to the minus 6 meters is equal to 1 micrometer. This is units conversion using stoichiometry. You see how meters and meters cancel out here?
Yeah. And it's just one nano thing. It's just one nano.
One micro. This is micro.
Oh, right.
Okay. So if I do this divided by this, so this is 412 times 10.
The calculator?
You actually don't need the calculator. You want to see how to do this without the calculator? You don't need the calculator.
All right.
Okay. What do I know, Ethan? For instance, if I want to divide two exponents, let's say I have like 3 to the 4th over 3 to the 2nd. Do you know what that is? Do you know how to simplify that?
I think you do it like 3 times 3 times 3 times 3, and then do 3 times over 3 times 3. I think it's something like that.
Yeah, that works too. So you can do 3 times 3 times 3 times 3 all over 3 times 3. And do you see how some of these would cancel?
Well, yeah.
Right? Do you see how this just becomes what? 3 times 3?
So then...
So it's just 3 squared.
6.
No. 3 times 3 is 9. But it's 3 squared.
Right, it's 9.
The other way to write this, Ethan, this is the same thing as 3 to the 4 minus 2. Anytime you have x to the a over x to the b, this is the same thing as x to the a minus b. You can just subtract the exponents if it's the same base. Okay?
All right.
So in this case, right, you see how I have 10 to the minus 9 over 10 to the minus 6? What's that going to become?
It will be 10 to the minus 9 minus negative 6.
Minus negative 6, very good. What's that going to become?
Which would then be like 10 to the negative 3.
Yes, good. 10 to the negative 3, good. Yes, 10 to the negative 3, okay? This becomes...
Oh, there's the amount.
There it is, 412 times 10 to the minus 3 micrometers. But then, I think I'd like to convert this a little bit, right? Because, okay, if I want to make this, like, get rid of this times 10 to the minus negative 3, all you have to do, right, is move this decimal to the place three times. This becomes
So that'll be 0.412.
micrometers. Yes, exactly.
And that's the final answer?
That's it. Congrats, dude.
Okay.
Nice. That's a cool question. That's actually pretty related to like what we were doing the other time. Don't forget about my Robux. Yeah, you kids, dude. Of course. All right. Cool. Thank you, everyone, for coming to this extended edition of Office Hours. How long do we stream for, dude? An hour and 48 minutes? Wow, I'm about to call Office 2 hours. It was good though. I liked it. No, we had the return of Ramton. I really enjoyed going through all of that eigenvalue, eigenvector stuff. That was really cool. I hope you guys got something out of that. I definitely did. I know Noise appreciated it. I did too.
Yeah, we can always go through more stuff like little by little. I feel like a lot of the times we just kind of open a can of worms and it's hard.
It's cool. It's great. No, I love it. And honestly, like we even got some people interested in the TikTok. They were asking. They were like, "Oh wait, why do I apply this?" You know. So yeah, it's cool. It's a balance. I like it. Because on one end, yeah, I want to help people with math and science questions, and you know we do that. Some of the stuff's basic and easy and cool, but then I also want to keep other people who are interested in higher level stuff to, you know, see some of the cool stuff, the applications of where it is. It helps everybody.
I mean, even if people don't understand it, I feel like that has pretty cool applications. Like,
yeah.
In the future, maybe we can talk about like Markov chains, Markov.
Ooh, yes, dude, Markov chains, dude. Wow, you're bringing back like all the buzzwords of like sexy physics that I forgot.
Also, I wanted to say something.
What do you want to say, dude? It's cool.
Isn't today the middle of the month for May?
Oh, it is. It is. Yeah, I need to do a supporters draw. Let me do it on the next one. I'm tired. I'm exhausted.
I should have just reminded you when you were gonna do my question.
Yes. Although I probably would have still been too tired. It's okay. All right. Cool. All right. Thank you everyone for joining. Had a fun time. Learned a lot with you guys. Appreciate everything. Next stream will be Wednesday, hour later, 4 p.m. 4 p.m. Pacific, 6 p.m. Central, 7 p.m. Eastern. Let me look at my calendar. I didn't expect to stream for 2 hours. Okay, I got like probably time for 1 or 2 Fortnite games because I gotta go teach at 7. So if you guys want to come join us and play Fortnite, we're gonna do that in the actual gaming channel. If you're in the Twitch, don't worry, you're just yeah. What's up? What's up? Okay, let me end the TikTok. Good to see you guys on TikTok. Please come by again to the next one. And that, and then we end the 1 sec. I gotta end the other one too.
And I'm gonna head out also because I have
Good.
to.
No, Ramton, I appreciate it. Yeah. Anytime you need to leave, Ramton, feel free to. You're super good. You're cool.
All right.
All right, dude. Feel better, man. I'll see you around.
Yeah, I'll see you Wednesday. We can do the thing this week. The podcast. Yeah, like last week, I was pretty busy, but now it's a lot better because. Cool.
I might have you I might have you host it yourself if you want to do it because I have to fly out to my sister's graduation this Thursday, but I'm more than happy to have you host it if you want to do it. Otherwise, we can do it again next week. You let me know.
Let me know how I can do that, but I'm definitely down to do that myself as well.
Cool.
Because thankfully I figured out a place and like
good dude.
The landlord seems pretty nice also. So.
He's not a scumbag.
It's a she, but yeah, like she seems pretty nice. Like
they always seem nice, dude, and then like the second you ask them to like fix the tub, they become the devil.
No, but she was like, oh, if there's any issues, just let me know for sure. Like, she herself like put the time without us asking to like go show us around and everything.
Oh, okay, that's nice.
At least